Number 18 gives us the graph of the derivative of f of x. So y is equal to the derivative of f of x on this graph. For what values of x between -3 and 3 does f attain or have a relative maximum, relative minimum? Justify your answers. So relative maximum, we need to ask ourselves, how do we normally do that? I know this is a different problem, but how do we find relative maximum? Well, that happens when the first derivative changes from increasing to decreasing, from positive to negative. Well, here we've got a graph of the first derivative, so we're going to kind of translate it down to a number line, because this is the way we're used to looking at it. So the derivative is equal to 0 at these 3 points, right? Because on this graph, the y is the derivative, so y is 0 at these 3 points. So at -2, 0, and 2, right? The derivative is 0 at those points. So normally we would fill this in by plugging values into a function to figure out if the derivative is negative or positive in between these zeros. Well, here we don't have to. We've got the graph. So if we look at the graph, this part of the graph right here is all positive. That's the derivative. So the derivative is positive at those points. Derivative is positive here because it's above the y-axis. And the derivative is positive here. So all of those values have derivatives that are positive. So when x is less than -2, the derivative is positive. When x is between 0 and 2, the derivative is positive. And when x is greater than 2, the derivative is positive. Then below there, this part of the graph, derivative is negative. The y value is negative for all those points. So in here, derivative is negative. So we're used to this number line. It may make more sense, but we kind of have to translate it from that graph that we're given. So relative maximum occurs when it changes from positive to negative. So that would be at -2. Relative minimum changes from negative to positive. So that would be when x is equal to 0. So we have to justify your answers. So we have a relative max at x equals -2 because function f, the original function, not this graph, but the original function changes. One too many e's there. It changes from increasing to decreasing. Maybe I didn't have too many e's there. Mr. Mitchell has forgotten. Just go. Can't read it on handwriting. Changes from increasing, positive derivative, to decreasing, negative derivative. So that's when it has a max. There's a relative minimum at x equals 0 because f changes, the original function changes from decreasing to increasing. Part B, for what values of x it is the graph concave up. So concave up is when the second derivative is greater than 0. So now we're looking at second derivative and we want to make a number line for that. This one's a little bit trickier. So the numbers we put on here are where the second derivative is 0. So what we need to think about here is second derivative is really just the derivative of this whole graph right here. So forget that it's a second derivative for a second. Just think of it as the derivative of this graph. We want to know when's the derivative of this graph equal to 0. Well, that's when the slope of the tangent line is 0. So that happens right here at x equals -1. It happens when x is positive 1. Derivative is 0. And the derivative is 0 when x is equal to 2. So those are the points where the derivative of this graph is 0, or in other words, where the second derivative is 0. Now we need to figure out what's going on in between these zeros. So remember, again, we're talking about the derivative of this graph. So the derivative of this graph talks about the slope, the rate of change, how it's changing, increasing or decreasing. So to the left of -1, this part of the graph is decreasing, right? The slope of the tangent line at any point on this part of the graph would be negative. So this is negative, second derivative over here. Then from -1 to 1, this part of the graph is increasing. Slope would be positive for every value in there. From 1 to 2, graph is decreasing. Derivative would be negative. The slope of the tangent line is negative. And then from 2 to 3, back to positive. It's increasing. So now we have a number line for our second derivative. We want to know when is it concave up. Well, it's concave up from -1 to 1 and from 2 to 3. Right? We're only going in this interval from -3 to 3. So it's concave up on those intervals because our second derivative is greater than 0. Concave up, second derivative is greater than 0. Alright, last part here asks us to find, or to sketch a graph, and it tells us f of -3 is 0. So we're going from -3 to 3. And our starting point here is at 0. Now the y values don't matter so much here. We kind of have some freedom as to where we put the y values. As long as our general shape is the same, we're good. So we're using these number lines and all this information along with where our maximums and minimums are and our inflection points, which would be all three of these, because they're changing from concave up to concave down or vice versa. So we're using all that information to sketch a graph. We have a maximum when x is -2. So at -2, it's going to have to be above our starting point. How far above doesn't make that big of a difference. Right? Then we have a minimum at x equals 0. So when x is 0, we're going to have a point low. We have inflection points at -1, 1, and 2. So at -1, that's between our maximum and minimum. We need to go ahead and put it somewhere in between there. We can put it on the x-axis, above or below, it doesn't really matter. I'm just going to put it below. Then we have an inflection point at 1, so it has to be above this minimum. Otherwise, if it was below, this wouldn't be a minimum. So it has to be above there somewhere, so I'm just going to put it up a little bit. And then we have another inflection point at 2. So again, this has to be higher than the last point, because if we did it lower, then this point would be a maximum, local maximum, but it's not. So I'm going to put it just above the x-axis. Now we're using these number lines, these intervals, to figure out what's happening with the graph. It's increasing to start, obviously, right? Kind of have an idea of what's going to happen. But now the biggest thing is looking at the concavity. So the concave down until we get to -1. So from here all the way to -1, concave down. Then from -1 to 1, concave up. From 1 to 2, concave down. And then from 2 to 3, concave up. So that's what our graph should look like. That's the graph of y equals f of x, our original function. Looks like that. That's what its derivative looks like.